Welcome to the ninth lecture of the ongoing course on matrix method of structural analysis. This and the next lecture is the concluding lecture of the review of structural analysis 1. What essentially we are going to do today and the next lecture is to put everything whatever we have reviewed so far, put everything together and in a bag, and then prepare ourselves for the journey for structural analysis through matrix methods. Okay, let us try to just recall what we have done so far. Reviewed. This is very important. I already repeated that many times, and probably throughout the course I will be repeating it many times. There are three important pillars of structural analysis. One is equilibrium. Equilibrium essentially tells us how the different forces are related to each other. So, this gives you how the different forces are related to each other, right? Now, then we have equilibrium, and then we have compatibility. Compatibility gives you or tells you how different displacement how different displacements are related to each other. Now, for statically determinate structure, equilibrium equations alone enough to solve the structure completely. For indeterminate structure, equilibrium equations not enough, then we need another equations which are compatibility equations. And then once we have the force and displacement, then the third pillar, the constitutive relation, which tells you how this force and displacement, how these two are related to each other. So, these are the three important that we have already mentioned many times. Now, you see, so we will shortly see there are, when we say the force or the displacement, there are different definition of what forces and what are the displacements, and how those different forces are related to different displacement, that we will see shortly as we move on. Now, constitutive relation essentially tells us that if we have a force, say this is force, and then we have a displacement, this is displacement, then constitutive relation tells us how these two different forces and displacements are related to each other. Now, based on how this relation is expressed, we have two definitions of this relation, or there are two ways we can express this relation. One is the flexibility definition and another one is the stiffness definition. Flexibility definition is what? Flexibility definition is, if you have a force, then that force is equal to, say, some A into D, that is, and then stiffness definition is D if we the displacement, this is stiffness definition, and the flexibility definition is this. So, we can use K here, that is the term that we will be using very often. So, let it is K, and then we have, say, A, which is essentially K inverse, which is equal to force, right, which is equal to force. Now, these two relations, this and this, they essentially tells us the similar thing, but in a different way in the sense whether with the knowledge of force we determine the displacement, or with the knowledge of displacement we determine the force. So, based on which definition we are using, whether it is the flexibility definition or stiffness definition, we have two class of methods. One is force method and one is displacement method. Force method, where the example of the force method is method of consistent deformation, where we use the flexibility definition, and then we have displacement method, for instance the slope deflection method, we use stiffness definition. Now, the displacement method now is further extended in the course. We will be extending the displacement method to have a more general method. Now, you see, but the premise, the concept that constitute the premise of the matrix method of structural analysis is this equation, this definition. But you know, the concept alone is not sufficient. The concept is important, but how the concept is translated into a method, that is also important, because you see whether the force method or method of consistent deformation or method of slope deflection method or moment distribution method, they all are based on flexibility or stiffness definition of force and displacement relation. So, the same concept will be using for matrix method of structural analysis, but the way this concept is being translated into a method, for instance for method of consistent deformation, slope deflection method, they lack the generality, they lack there is a huge the way it is translated, that puts a huge restriction on the applicability of the method for a larger class of problem. And more importantly, that if you recall the many operations that you performed in structural analysis 1, even with the same concept, all the operations you performed manually, we had to do it manually. But then for a larger structure, we really cannot do all these calculations, manual calculations. So, we need a method which can be translated into computer code as well. So, that is the major motivation of looking beyond structural analysis 1. Now, but if I have to tell you the concept wise are they different, really they are not. It is the similar concept, but the difference lies in the way the concept is translated into a method. Okay. Now, so now you see, for instance, suppose if we take a truss. Okay. Now, if you recall the very first lecture that was the introductory lecture, I tried to give you a general overview of the philosophy of matrix method of structural analysis, and there we discussed the essence. The essence is if you have a structure which may be very complicated, very large, there are many members in the structure, different joints. But we don't solve the structure, we don't analyze the structure as a whole. What we do is we break the structure into small pieces and then write equations for all the pieces, and then we relate those different pieces. We write equations which gives us how the different pieces are related to each other, and that relation gives us the global system of equation which we need to solve for the entire structure. So, but then here two important part in this method. One important part is, or rather three important part. The first important part is break the entire structure into different pieces, different members. This is the first thing, and the second thing is write equation for each different parts, and then third is you assemble all these pieces to get the global to get the equations for the entire structure. Now, what we do is the second step, we just try to understand the second step in the context of structural analysis here. Now, you see, for instance, when we do that, we will realize that the second step, the concept is essentially the same that we have learnt in structural analysis 1 and also reviewed in the first 8 lectures of this course. Okay, so consider a truss. It could be any complicated structure, determinate, indeterminate structure. Here another important point is, though what we learned in structural analysis 1 is this displacement method, force method we learned while solving indeterminate structure. For determinate structure, just equilibrium equation was enough. But again, in matrix method of structural analysis, it's nothing like that. It has to be applicable for only determinate structure or indeterminate structure, or for only indeterminate structure we go for matrix method of structural analysis. It's nothing like that. Irrespective of the fact whether the structure is determinate or indeterminate, we can apply this method. Okay. Now, but again the structure has to be stable. Now, take an example. We have a truss here. It is determinate truss. You can easily see. But again, as I said, it is the concept is true for any structure with any number of members. And now take for the first, you consider the structure itself, remove all the loads, different loads, only the structure. Now, the first step is to remove, is to divide the entire structure into small pieces, and these are the small pieces. Okay. Now, here we have 3 members, so it is divided into 3 parts. You can have n number of members. If it is a plane truss, if it is space truss, then the members will be oriented in 3-dimensional space. It depends on the problem we are considering. Okay, so once we have different parts of the structure, the next step, if you recall, next step is to write equation for each part. And what is that equation? The equation is the force displacement equation. So, what we do is we write equation for this part. This part, what we write equation is your the force is equal to stiffness into displacement, right? And here also we write the same part, that force is equal to stiffness into displacement, right? And for this part also we write the same thing, force is equal to stiffness into displacement, right? We already know how to write force is equal to stiffness into displacement. If you recall, all the methods that we now just reviewed, they also based on the similar equation. Same equations we will be using for this method as well. But now, since we have to divide the entire problem into small pieces. So, we have to write this equation for every pieces, and once we have written this, then we will assemble all these equations. So, we will get an equation, say we will get this equation from this member, we have a set of equation for this member, and then we have a set of equation for this member, and then we combine all these set of equations to get the equations for the entire structure, and then we solve it, right? Now, but how to write equations for what would be the form of the equation for truss or for different other members, for different other structure, for instance for beam or frame or any other structural components, that we will see as we move. Now, take an example of say beam. Now, we have to divide the entire into small parts. Let us take here, in this case we divide into 2 parts. One is part AB, and then another is part BC. So, this is part AB, and this is part AB, and this is part BC, right? A, B, then B, C. Then we have to write force displacement equation for this. So, we write that force is equal to stiffness into displacement. For this, I will give you an example, taking a very simple structure. Force is equal to stiffness into displacement for these as well. Okay. Now, again, once we have this set of equation for this member, and then this set of equation for this member, we assemble them. We write an equation which relate these different parts, okay, and then we get a system of a global equation, and then we solve that global equation. Take one more example. For instance, if we take an example of this case, now here also we do the same thing. We have a member here which is AB, say this is A, this is B again, then we have another member here which is B and C, and then we have another member here C and D. Okay. Now, again we write the force displacement equation for this, force displacement equation for this, force displacement equation for this, and then assemble them to get the equations for the entire structure. So, this is the philosophy that we will be using. Now, the detailed discussion on how these equations, force displacement equations to be written for different members, and how to consider, for instance, you see in this case, for instance, if we see the previous one, the beam case, all these members are horizontal members. So, their orientation, the orientation of all the members, the AB and BC, they are same. But again, for this structure, the orientation of different members are different. Even for this structure, you will see orientation of different members are different. BC is horizontal, AB and CD are vertical members. Now, then we will discuss how these equations to be written for each member, and when we write these equations, how the orientation of the different members to be considered, and then once we have considered the orientation of the different members, then when we assemble it, then how this orientation needs to be considered in the assembling stage as well. That we will discuss in detail. Now, let us give you an example of the same problem here, the truss problem. For instance, suppose to write these, as I said, for every member we have to write the force displacement equation. Let us consider one truss member and then see what is the force displacement relation for this member. Here idea is really not to give a detailed derivation of the force displacement relation, or this because that we will be doing anyway in the subsequent weeks. The idea is to make some points which are important and which we need to keep in mind when we actually do this exercise in detail. Okay, so take any member, say in this case if you take member AB. So this is member AB. Okay. So this is now another important thing is we will see that when we actually divide the entire problem into small pieces, we do not use the A member A, B member B, C or member C D like this. We write this is joint number 1, this is joint number 2, this is joint number 3, and again these are the joints, and this is a member number 1 and this is member number 2. Member number 2 and member number 3 like this. Okay. So, suppose this is joint number 1 and this is joint number 1 and this is joint number 2. So, take this member, this is joint number 1, this is joint number 2. Now, you see the truss member, we know that truss members are the two force members. Two force members means it has the force along the longitudinal direction of this member. The truss member is either subjected to axial compression or axial tension. So, if it is the forces are either tension or the forces are either compression. If we take this is 1 and this is 2, the forces would be either compression. Okay. Either forces compression and tension. Okay. Now, once it is applied, when irrespective of whether it is force is with the compression or tension, the force is always along the axial direction of the truss, right. Suppose that force is F. Suppose that force is F, and then suppose the cross sectional area of this truss is A. Okay. Then the definition of stress that we have, the sigma, that if we take any cross section, that any cross section stress is equal to force divided by area. Now, it is you put a star mark here. The reason I am asking you to put a star mark here, because you see this is the definition of stress that we learned in our school, and the same definition we will be using here. But you know, this is not the only definition of stress. For instance, here stress has two important parts. It depends on two important parts. One is the force and another one is the area. Now, which force we are talking about, or we are considering, or which area we are taking, depending on that there could be different measures of stresses. So, as we see in other courses, for instance the course on elasticity or then course of nonlinear mechanics, we will see that there are different measures of stresses and how these stresses are different depending on the what force and what area are using for the definition of stress. Now, then suppose this force is F, now under the action of this stress, suppose, or the force, suppose the change in length, suppose original length of the member is L, this is member length L, this is member length L. Suppose the change in length, it could be the extension, it could be the under tension or under compression. Suppose the change in length is delta L. Suppose change in length is delta L. So, if change in length is delta L, then we know the strain is equal to delta L by L. So, if it is tension, then delta L is positive. If it is compression, this shortening takes place, then delta is negative, automatically strain is compression. Now, again here also you put a star mark here, because you will see in the subsequent courses there are different measure of strains as well. So, but the definition of stress and the definition of strain that we are using here is this. Okay. Now, once we know what is stress for this and strain for this, then stress strain relation is essentially the constitutive relation, and the stress and strain is related through Young's modulus. So, we know that sigma is equal to Young's modulus strain into epsilon, right, strain into epsilon. Now, if I substitute the value of sigma and epsilon here, then what we get is this. So, this becomes F by A. F by A is equal to E is the Young's modulus and L is equal to delta L by L. So, this gives us a very important equation, that is equal to F is equal to A E by L into delta L. Okay. Now, let us not use delta L here, because the reason is, instead of delta L you can use U here, because that is the definition of displacement, that is the way, that is how we will define displacement in the subsequent lectures. So, let us right from the beginning we stick to the notation. So, let us this is U is the displacement. So, this is U, this becomes U and this becomes U, and then this is so U is the displacement, okay, and strain is equal to U by L. So, this is, now look at this, what is essentially this? This is essentially your stiffness definition, where the force is equal to something multiplied by displacement, and this something K in this case is equal to A E by L. This is the stiffness for this member. Okay. Now, but you know, okay, this is the stiffness of this member. Let us now see in a more general case in the sense, take the same member, but you see, you remember this is force is equal to stiffness into displacement. Now, then what is important is, what are the forces you are considering and what are the displacements components we consider in our analysis. Now, what is U here? U is the change in length, right? If the original length is L and the U is the change in length, and force is equal to, because of this change in length, what is the force, or because of the force, it is the change in length. But really, suppose consider a situation where you have, but when we say U is some value, we cannot really say then how much is the movement of, suppose how the change in length can take place. Point 1 in this case, point 1 moves in this direction and point 2 moves in this direction. Similarly, in this case, point 1 moves in this direction and point moves in this direction. And what is the net movement between point 1 and 2? Net change between point 1 and 2 is U. But when we say U, you cannot tell us that what is the movement of point 1 and what is the movement of point 2 separately. Okay. Now, let us take the more general case where we don't write this equation in terms of net change in length. Instead, we write this equation in terms of the movement of point A, or the displacement of displacement is the correct word in this case, the displacement of point 1 and the displacement of point 2. The net displacement would be u, but let us write the same equation in terms of not the net displacement, write the equation in terms of net displacements at u at 1 and the net displacement at 2, right. So, if you do that, so take once again this, suppose in this case you draw these once again. This is AB. Now, this is point number 1, this is point number 2. Now, suppose U1 is the suppose U1 is the movement of, this is point number 1 and this is point number 2. Okay. Now, suppose U1 is the movement of point 1 and U2 is the movement of point 2, but still U1 and U2, the direction of U1 and U2 is along the line, along AB. Okay. So, U1 is this movement of 1 in this direction and in this direction, and U2 is the movement of 2 in this direction. Okay. Now, suppose U1 and U2 are the movements of point 1 and 2. We will have more general case, more general than this, that will come, where the U1 and U2 not in the direction of the line of action of the force, rather not along the longitudinal axis of the member, rather we have a different coordinate axis for defining U1 and U2. There we will discuss what is the local coordinate, global coordinate in details. Okay. So, U1 and U2 are the displacement, and corresponding force is F1. F1 is the force at F1 at node number 1 and F2 at the force in F number 2. Recall the spring problem, where we had just one force and the one displacement, and one force and one displacement related to the spring constant. Recall just now the previous example, where we had just the net displacement and the net force, means one component of displacement, or rather one definition of displacement and one definition of force, and these definitions are related to the stiffness of the member. But now here we have two displacement, two displacements and two forces. Then we have to find out how these two displacements are related to two forces. Let us do that here. So, we will do that in a separate, again applying the principle of superposition, where we assume first there is no movement of point 2, there is no movement of point 2, the point 1 moves, and then write the equation, and then assume that there is no movement at point 1 and the point 2 moves, write the equation, and then we add these two equations to get the total moment at point 1 and point 2. Now, so this is now divided into two parts. So, this is equal to one problem, this problem, where this end is fixed and the point 1 is allowed to move. So, this point may move, this point may move, say this is U1, this is U1, and suppose this is and then plus another problem where this point is fixed, and then we have this movement of point U2. Okay. This plus this gives us this, right. Now, when let us find out what are the corresponding forces. The corresponding forces are now is suppose this is let us write this is P1 dash and this is P2 dash. This is P2 dash, and similarly here it is P1 double dash and this is P2 double dash. Okay. Now, so this problem plus this problem gives us this problem. Okay. Now, let us write the equation for this is equation for this and equation for this. So, equation for this will be, the first one will be, say P1, if you recall, P1 dash will be AE by L into E1, and similarly P2 dash will be minus AE by L into E1. The minus is because if you apply a force, in this direction, reaction will be in opposite direction. But since we showed we are taking as per our sign convention, if we assume this force is positive, so naturally opposite will be negative. So that's why it is negative. Now similarly, the P2 dash will be, so if we write P2 dash, so P1 dash and P2 dash. So we have P1 double dash if we write. So P2 double dash is equal to, it will be AE by L into U2, because it is in the direction of U2, and then P1 double dash will be negative minus AE by L into U2, right. So, now look at here P1 and U2, P1, okay. So, because if we apply P2 will cause displacement in this direction and the resultant force will be in opposite direction, but we have taken P1 in this direction, that is why it is negative, right. Now, you see if we add them, then we get this, right. If we add them, then what we get is the total force is equal to the F1 is the force applied at node number 1 and F2 is the force applied at node number 2. So, F1 will be P1, this plus this will be F1, and this plus this will be F2. So, if we write F1 and F2, then what we have is, if we write here that F1 is equal to we have P1 dash plus P1 double dash, P1 dash plus P1 double dash, and similarly F2 is equal to P2 dash plus P2 double dash. Now, if we substitute P1 dash here and P2 dash here and write in a matrix form, then what we get is this. So, let us erase everything. What we get is this. We get that F1 and then F2 is equal to, or matrix, this is U1 U2, and this we get A by L minus A by L, and then this is also minus A E by L and A E by L, A E by L. Or if we take just write the same equation, if we write quickly F1 and F2 taking A E by L common, or if we can take A by L common, then it will be A by L, A by L, this is 1 minus 1 minus 1 and 1, okay. And then U1 U2, U1 U2. Now, this is essentially K and this is essentially F and this is essentially D. So, you see the same stiffness definition we have for one member. Now, similarly, similar equation we can have for this member and then assemble it, but then the process is not that straightforward. So, what we will do now is the idea has been to that exercise doing the same, writing these equations for all the members and then assembling it, solution of all these members, that will be doing in detail in the subsequent weeks. Okay. But here the objective, the idea has been for this lecture has been to tell you, see, look, this is the way we can write the force, we can write force displacement relation for a given member, and the similar thing you can do it for beam or frame structural component as well. But then these equations are the building blocks of matrix method of structural analysis. So, when we but again another important thing, you look at all these equations are written in terms of matrices, right. For the stiffnesses matrices, when we solve this equation, essentially we have to do several matrix operations. That is the reason why next week we will be having a brief review of matrix algebra. Okay. And then on the fourth week, when we start solving or formulating the method for Truss, we will start with this equation, this force displacement relation, and then see, just now I said that what are the definition of the what are the direction of the displacement or the direction of the forces you are considering. Depending on that, you have the stiffness matrix, because stiffness, when we talk about the stiffness, it always relates to force and displacement. Therefore, it is important that what forces we are taking and what displacements we are taking, that definition needs to be properly given. In the previous example, where we had just the one displacement component and the one force component, it was the net displacement of the net change in length of the member. In this case, it is the U1 and U2, the displacement at node 1 and the displacement at the node 2, but they are in the direction of the longitudinal axis of the member. And then again in a more general form, we will see that instead of writing the equation in terms of displacement along the longitudinal axis, why not write the equation in terms of displacement with respect to certain global coordinate, means the horizontal displacement and the vertical displacement irrespective of the configuration of the member. Always write the equation in terms of horizontal displacement, vertical displacement, and the horizontal force and the vertical force, and then we will see, and there we have to incorporate the orientation of the member. Now, that we will do in fourth week. So, I will stop here today. In the next class, which will be the concluding class for this review, will not repeat the similar exercise for beams and frames, but we will try to understand what are the different displacement components we can have for beams and frames, and then conclude this review. Okay, see you in the next class. Thank you.